In this video, we're going to work example problems related to isosceles triangles, as well as the main auxiliary lines that we use to analyze triangles. So the angle bisector, the median, the altitude, and the perpendicular bisector. All right, let's get started. If segment VU is congruent to segment VT, then what type of triangle is triangle VTU? Well, that means it's an isosceles triangle because two of the legs are congruent. Scalene triangles are when no legs of the triangle are congruent. Equilateral is when all the legs are congruent. Isosceles is when two of the three are congruent. If segment VU is congruent to segment VT, which angles of triangle VTU are congruent? Well, we proved a theorem in the textbook that showed that the base angles of an isosceles triangle are congruent. And what that notation is referring to is, with an isosceles triangle, the angle that's included between the two congruent sides is the vertex angle, and the two other angles are the base, or what's called the base angles. Those two angles, the base angles, are congruent. So in that case here, if VU is congruent to VT, that means V is the vertex angle and T and U are the base angles. So angle U, or angle T, is congruent to angle U. All right, if angle T is congruent to angle U, which sides of triangle VTU are congruent? So yeah, we proved the theorem that we used to answer this question in both directions, and it's reversible. So if we started with this triangle that we didn't know what it was, and we proved that these two angles were congruent, then that means it must be isosceles with the sides opposite those angles being congruent. You can't have one without the other. So if you can prove that two legs of a triangle are congruent, that obviously means it's isosceles, and the angles opposite those sides are congruent, or the reverse. If you start by showing that two angles of a triangle are congruent, that means the triangle must be isosceles, or maybe equilateral if all three are congruent. So this would mean that segment VU is congruent to segment VT, side VT. All right, if VU is congruent to VT, VU is equal to 10 and TU is equal to 8. What is the perimeter of triangle VTU? So perimeter, we learned that the perimeter of just thinking about, we just talked about polygons. The idea of the perimeter of a polygon is you add up the lengths of all the sides, regardless of if they're the same length, side lengths or not, whatever. You just add up all the side lengths and you get this number. That's a property of a characteristic of a polygon. It's called the perimeter. You can do this for any polygon with any number of sides. So with a triangle, we're just adding up the length of the three sides. So if they're saying if VU is congruent to VT, okay, and VU is equal to 10 and then TU is equal to 8, well, then that's easy because we have VU and VT are both equal to 10 because VU is congruent to VT. So 10, the perimeter P is 10 plus 10, and then they give us this side length TU. So P is equal to 28. All right, if VU is congruent to VT, so for every one of these problems, we'll have VU congruent to VT, okay, and the measure for this first question, and the measure of angle T is 69 degrees, find the measure of angle U. Well, that's another base angle. That's going to be 69 degrees. Okay, if measure of angle T is 69 degrees, again, then what's the measure of angle V? Well, okay, that means that this must be 69, so we did the sum, these angles must sum to 180. So let's see, 70 times 2 is 140, minus 2 is 138. So 69 times 2 is 138, so 180 minus 138 is 42. So that would be 42 degrees. All right. So again, VU is congruent to VT. If the measure of angle T is 72 degrees, find the measure of angle V. Well, the same idea. This is going to be 72 degrees. So what's 72 times 2? That would be 144. 180 minus 144 is 36. Okay, VU is congruent to VT. Measure of angle V is 40 degrees. So now find the measure of angle T. Well, okay, it's just these are going to be the same angle. So it's 2x plus 40 is equal to 180. So subtracting 40 from both sides, dividing both sides by 2, you get x is equal to 70. Measure of angle T is congruent to the measure of angle U. All right, determine whether the sets have a subset relationship. Are the two sets disjoint or equivalent? Do the sets intersect? All right. So we're in this first problem, we're comparing the set of equal lateral triangles to the set of equal angular triangles. Okay, well this we know that we proved we were shown two corollaries that show that all equal lateral triangles are equal angular and all equal angular triangles are equal lateral. So it's the same set here. The set circles would just lie on top of one another. They're equivalent sets. There's no subset relationship. They're equivalent. One is not contained within the other. It's the same exact set. If you have an equilateral triangle, then it must be equiangular. If you have an equiangular triangle, it must be equilateral. Okay, the set of triangles with two congruent sides and the set of triangles with two congruent angles. Same exact idea. This is the same set. These are equivalent sets. They lie on top of one another. If you have an isosceles triangle, which is that's a triangle with two congruent sides, then it must have two congruent angles being those base angles. And same idea in the other direction. If you start by showing that there's two congruent sides or two congruent angles, then that means the sides opposite those must be congruent. And now, but this extends to equilateral. So I guess equilateral triangles would be, I'm not sure what they're saying here, but I'm assuming that equilateral triangles would be included here because equilateral triangles have two congruent sides. They have three, but that means they have two, right? So, but that also means that they have to have more than two or more congruent angles. So it's the same set. All right, right triangles and obtuse triangles. The set of all right triangles, the set of all obtuse triangles. Okay, these sets are disjoint, meaning that they're completely separate and that there's no right triangle that is an obtuse triangle and vice versa. Because a right triangle is going to be a triangle. What's the definition of a right triangle? It's a triangle to where one of the angles of the triangle is 90 degrees. It can only be one of the angles. You can't have two angles be 90 degrees in a triangle because then the third angle would be 0. So it's just going to be one angle is 90 degrees. Okay, an obtuse triangle is when one of the angles is obtuse. But then you can't have an obtuse angle and also have a right angle. So there's no mixing here. All right, isosceles triangles and right triangles. All right, so these are going to intersect, but it's not going to be a subset relationship because, okay, we can have a right triangle be isosceles. It can't be equilateral, but it can be isosceles. There you go. We talked about how this means that these angles are going to be 45 degrees, the acute angles. Okay, but not every isosceles triangle is going to be a right triangle. We've been working examples so far that showed that. So this is an intersection relationship. You have some isosceles triangles that aren't right triangles, like shown here, but you also have some right triangles that aren't isosceles triangles. Like shown here, these two, none of these sides are congruent, so that would be over here. And then there's some that are both, like this. Describe the line segment as determined, underdetermined, or overdetermined. Use the accompanying drawing for reference. Okay, It's really important that we understand the meaning of something that's properly determined or properly constrained. That's another way of saying it, properly constrained. So what does under constrained, over constrained, and just properly constrained mean? This is important because if we're going to add an auxiliary line or figure to some scenario for analysis, it needs to be properly determined, properly constrained, or else what we're doing won't make any sense. So, okay, first, it says draw a line segment through point A. So if we're analyzing some situation, this could be in engineering, could be in any scenario, and we're going to say, okay, look, I want to add this auxiliary figure here to analyze something geometrically. Okay, so all right, I'm going to let's say I draw a line through point A. I'm going to draw a line through point A, and I do that. Well, okay, if I'm giving a presentation to a group, someone might say, well, wait a minute. Well, what else is there about that line? I mean, what is it? Is it parallel to another line? What? I need more information because why didn't you draw this line? Like, what line are you talking about? Is it a horizontal line? I mean, there needs to be more information. That's underdetermined, under constrained. Just saying you're going to draw a line through a point with no other information, that's underdetermined, under constrained, because there's an infinite number of lines that go through a point. So I can't just draw this line here and say, here's a line through point A and start giving dimensions and references to this line because, well, what's this line? You see? So that would be under constrained. Okay, draw a line segment with endpoints A and B. So line segment with endpoints A and B. That would be properly constrained. That would be just the determined case because it's a unique line. The figure that you add, any auxiliary figure that you add to something needs to be unique. There's only one line or figure that satisfies those constraints. There's only one line that, like we talked about this in chapter 1, two separate points define one unique line. Two separate points. So this is the only line segment. We know what these points are. That's why they're there. So we know where point A is, where point B is. There's only one line that can go through those 2 points, or one line segment that can have those 2 points as an endpoint. So that's properly determined, properly constrained. Okay, draw a line segment AB that's parallel to line M. That it would be overdetermined, overconstrained. Because how can I draw a line segment that's both has the endpoints A and B and is also parallel to line M? It's not that that's not possible. It's just you need more information. You can't just the point they're making here is that you can't just say, look, I've got these 2 points in space. I know where those points are in space, but I don't need to tell you where they are. I'm just telling you they're 2 points in space. And there's this other line M that's somewhere in that same plane of those 2 points. Okay? Now I'm going to draw a line segment with endpoints at A and B parallel to line M. That's not enough information. You'd say, well, wait a minute, that's over constrained because, well, then are you telling me those 2 points are like contain a line that's parallel to line M? Otherwise, how can you say that? Because maybe the line that defines those 2 points isn't parallel to line M. I mean, maybe it is. It's possible that it is, but in just talking in general, it's over constrained, over determined. Okay, draw a line segment AB that's perpendicular to M. Same exact case as before. Over constrained. Draw segment AB so that line M bisects AB. Yes, over constrained. Without stating something about the orientation of line M, that's over constrained. That's in general, that's over constrained, over determined. Now, but if we said draw a line that goes through point A that's parallel to line M, well, we know we can do that. That would be properly constrained. Okay, a line from A perpendicular to M. So yeah, we've talked about this before. There's going to be a unique line. There's always a unique line that's either parallel or perpendicular to another line that passes through a point That's not on that line. So this would be properly constrained, properly determined. Given that triangle ABC is isosceles with AB congruent to AC, give the reason why triangle ABD is congruent to triangle ACD if D lies on segment BC and these criteria here. So, okay, let's draw this triangle. So we've got triangle ABC with AB congruent to AC. Okay, now if we have point D lies somewhere on BC, and it's the case that triangle ABD is congruent to triangle ACD. So like, okay, if this was point D, then we would have, they're saying that you'd have these two separate triangles, right? ABD and ACD. But they're saying that, okay, but D is at a point such that triangle ABD is congruent to triangle ACD. So this wouldn't be the location of D. So if it's the case that the two triangles are congruent, state why AD is an altitude, a median, and a bisector of this angle BAC, angle A here. So yeah, we've talked about this. We know that. We saw a theorem that stated that if you have an isosceles triangle and you add an auxiliary line, an angle bisector coming from the vertex angle of the isosceles triangle, going down to the opposite side. Okay, so this is an angle bisector. That's a properly constrained auxiliary line I just added. So here's point D. But with that, I can't make any statement about where point D is. If it's the midpoint of BC, if this is perpendicular, this is properly constrained. I just added this auxiliary line here, going through point A and bisects the angle BAC. That's it. Okay. But we talked about in the case that when you have an angle bisector coming from the vertex angle of an isosceles triangle, it separates the triangle into two congruent triangles. That's a theorem. So this is true. This is true based on the theorem we talked about. Okay? So with that then, if triangle ABD is congruent to triangle ACD, then, okay, so these two sides are congruent, right, in terms of comparing the triangles. This is the same side. But then, okay, BD corresponds to CD, so these two sides are congruent. Well, look, that means that point D is the median. It's the median line of triangle of going through vertex A, triangle ABC. So it's the angle bisector and it's the median. Okay, well, but what else? Well, angle B corresponds to angle C, and then angle BDA corresponds to angle CDA, so those are congruent, but this is a straight angle overall, so this has to be two right angles. So look, it's also the altitude, and it's the perpendicular bisector. Is it possible for a triangle to be an acute isosceles triangle? Yes. That's the kinds we've been looking at primarily. An acute triangle is when all the angles are acute angles. Well, look, all these are acute. That's isosceles, so yes. What about obtuse? Yes, yes. You could have something like those are the same side length. There's the obtuse angle, and those are congruent, so yes. An equal angular isosceles triangle. No. I mean, I guess it depends on how you look at it, because I guess an equal angular triangle has to be equilateral. So if you're saying that, well, since isosceles triangles are kind of like a subset of equilateral triangles, then maybe so. But technically, no, because if it's equal, again, equal angular means that it's also equilateral. It has to be. So I guess you wouldn't call this isosceles, even though there are two congruent sides. You call this equilateral, so no. In concave quadrilateral ABCD, the angle at A measures 40 degrees. Okay, this concave quadrilateral here. Here's the reflex angle. Triangle ABD is isosceles. Okay, with which sides are congruent? BC bisects angle ABD, and DC bisects angle ADB. What are the measures of angles ABC, angle ADC, and angle 1? Okay, so they don't tell us. I mean, it looks visually like these are the two congruent sides, but they don't officially say this. But I guess we could deduce that if this was a base angle, 40 degrees was a base angle, that means this would be, let's say, 40 degrees. Then the other angle would need to be, let's see, 40 plus 40 is 80. 180 minus 80 is 110. Well, this can't be 110. This is an acute triangle. So with that, we can make the statement that these are the legs, and this is the base of the isosceles triangle. So we can let's start by getting what these angles are. Why not? So, okay, if this is x and this is x, then we've got x plus x is 2x plus 40 is equal to 180. So 2x is equal to 140. X is equal to 70. Okay, but they tell us that BC bisects ABD, and so does DC. So that means that this is 35, this is 35, this is 35, and this is 35. Okay, now what we can see from here is that triangle BCD is isosceles with these two base angles. So these two sides are congruent. Okay, so, well, wait, it says angle, what's the measure of angle ABC? So we got that answer. Angle ABC is 35 degrees. Angle ADC is 35 degrees. So there's two answers there. Okay, now we just need to get angle 1. Well, we can get angle 1. 35 plus 35 is 70. What is 180 minus 70? 110. So angle 1, yeah, the measures of angle 1 is 110. There you go. All right, find the measure of angle 1 and the measure of angle 2 if the measure of angle 3 is 68 degrees. So we can see with these marks here that this is an isosceles triangle with vertex angle 1 and angles 2 and 3 base angles. So we know that angle 2 is congruent to angle 3. So therefore, the measure of angle 2 is 68 degrees, because that's the measure of angle 3. And then the measure of angle 1 is just going to be 68 times 2, and then subtract 180 from that. So 180 minus 136, 10 minus 6 is 4, 7 minus 3 is 4. So the measure of angle 1 is 44 degrees. Okay, if the measure of angle 3 is equal to 68 degrees, find the measure of angle 4, the angle formed by the bisectors of angles 3 and angles 2. Okay, so yeah, they're saying that these two angles are congruent, and these two angles are congruent. They just told us that these were the bisectors. But we can see this is isosceles, so that means these two base angles are congruent, so that means all of these angles are congruent. All four of these. Okay? Now, if the measure of angle 3 is 68 degrees, then that means that these angles are 34 degrees. Yeah, the problem we just worked was just like this. So, what's the measure of angle 4? Well, it's going to be 34 plus 34 plus measure of angle 4 is 180. So 34 times 2 is 68. So what is 180 minus 68? 112. Find the measure of angle 5, which is formed by the bisectors of angle 1 and angle 3. Again, let the measure of angle 3 be 68 degrees. So, okay, these two angles are congruent, and this is 68 degrees, so these two angles are 34 degrees. Okay, now, since this is isosceles, we got the same situation here. Okay, but now let's get angle 1. So if each of these are 68 degrees, then 68 times 2 is 136. 180 minus 136 is 44. So this is 44, angle 1. So each of these are 22. Because we know it's an angle, they told us it's an angle bisector. And so there we go. So 22 plus 34 is 56. So now what's 180 minus 56? 124. All right. Find an expression for the measure of angle 5 if the measure of angle 3 is 2x and all of these line segments bisect the angles. So yeah, it's just what we've been doing, but now we're going to use these variable expressions here. So we know that these two angles are congruent. These two angles are all four of these angles are congruent. We know that this is another bisector, but it's not necessarily the same here because this is an isosceles triangle. Okay, and let's see. So if this is 2x, 2x divided by 2, this is x, this is x, this is x, this is x. Okay, but now we've got 2x plus 2x is 4x, plus, let's say this angle 1 is y, plus y is equal to 180. So y is equal to 180 minus 4x. So 180 minus 4x. But if you divide that by 2, you get 90 minus 2x. So this is 90 minus 2x, and so is this. And there we go. So now we can say that if we take x plus 90 minus 2x plus the measure of angle 5, that's going to be 180 because you have a triangle here. So x minus 2x is minus x. Okay, measure of angle 5, add x to both sides, subtract 90 from both sides. There you go. In isosceles triangle ABC with vertex A, not shown, each base angle is 12 degrees larger than the vertex angle. Find the measure of each angle. So let's draw this isosceles triangle ABC with vertex A. So do like that. Each base angle is 12 degrees. Oh no, it's 12 degrees larger than the vertex angle. So if the vertex angle is x, then each of these is x plus 12. Find the measure of each angle. So, okay, x plus 12 plus x plus 12 needs to be equal to 180. So x plus x plus x is 3x. 12 plus 12 is 24. 180 minus 24 is 156. So x is 52 degrees. So measure of angle A, the vertex angle is 52 degrees, but then each base angle was just 12 degrees more than that. So measure of angle B is equal to measure of angle C is equal to 64 degrees. Okay, in isosceles triangle ABC, not shown, the vertex angle A is 5 degrees more than 1/2 of the base angle B. Find the size of each angle of the triangle. So, okay, similar problem to what we just did. We've got this isosceles triangle ABC with vertex angle A. That means that these two sides are congruent. Okay, the vertex angle A is 5 degrees more than 1/2 of the base angle B. So in that case, we're going to say that the base angles are both the same. They have to be. And then the vertex angle is 5 degrees more than 1/2 of the base angle. 1/2 of the base angle, 5 degrees more than that. There we go. So now find the measure of each angle. Well, okay, we have 1/2 x plus 5 plus x is equal to 180. So 2x plus 1/2 x is what? So that's 4 over 2x plus 1/2 x. That's going to be 5/2 x. So 5/2 x plus 5 is equal to 180. 5/2 x is equal to 175. X is equal to 175 and then 2/5 like that. So 175 divided by 5 is 35. 35 times 2 is 70. So, okay, the base angles, measure of angle B is equal to measure of angle C is equal to 70 degrees. And then the measure of the vertex angle is 1/2 of 70 is 35 plus 5.